From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone, and I will remind you, although I'm sure it's not necessary, but remind you that you do have homework due today. And for those of you out watching us on TV, I know there's some question on just when the homework's due. Well, the homework assignments are related to the lecture numbers, not necessarily the dates for you out there, because I know you get the lectures at a different dates. But like the first homework is associated with lecture number 4, and the second homework will be whichever day you hear lecture number 6 is when the homework's due, and so on. Well, I have gotten a few emails from those of you watching this on TV, and I got one from Dan up in Seattle. And I understood most of his email, but there was a portion that I didn't understand, so let me read it here. It says, "I'm a Utah Utes fan." Does anyone here have any idea what he's talking about? No, I don't know either. I checked it in Microsoft Word. I checked the spelling, and it wasn't in the dictionary. So Utes. I don't know. I'm not sure what he's talking about, but anyway, thanks for the email anyway. Okay. Last class we were talking about the Stokes parameters. And we had gone through the definition of the Stokes parameters. And maybe we'll have to have special exams for fans of Utah Utes. So think about that a little bit. Anyway, we're talking about the Stokes parameters. And let's go back and look at them more carefully now. And first, let's just write down a couple of equations for elliptical polarization. We said E sub x is some A sub x cosine kz minus omega t in the x direction. And we would have here that E sub y is A sub y cosine of kz minus omega t plus, we said, some phase phi in the y direction. And E sub z, we're going along the z-axis, that's equal to 0. And we said, we didn't prove it in class, but I'm sure all of you have proven it by now to yourself, that E sub x over A sub x squared plus E sub y over A sub y squared minus 2 E sub x over A sub x E sub y over A sub y cosine of phi was equal to the sine squared of phi. Now, how many of you proved this to yourself? Lots of hands out there in TV land. Oh, actually, there are a few hands up. Okay. And I gave you a drawing. We haven't looked at it yet, but let's take out this drawing that I gave you a class or two ago, where we just have plotted this for different values of phi. And so we said that when phi was equal to 0, we have linear polarization and going along like so. And for phi greater than 0 but less than pi over 2, we have elliptical at some angle here. And then when phi was equal to pi over 2, we have the axes of the ellipse were lined up with the x and y axes. And going around here clockwise. And then between pi over 2 and pi, we still had it going around clockwise, but some orientation like this. Finally, when we go to phi is equal to pi, we get back to linear, but now it's in some direction like this. And then as we go through here, phi greater than pi, but less than 3 pi over 2, now it's going in a counterclockwise direction. And 3 pi over 2, again, we're lined up with our axes, counterclockwise. And between 3 pi over 2 and 2 pi, some orientation like this, again, counterclockwise. And then when we get to 2 pi, we're back here, the equivalent to phi being equal to 0. So that is a plot of what the ellipse looks like here for different values of phi. Now let's go back here to the Stokes parameters, and we're going to play with them just a little bit and see what they mean more. So the first one we had, if we remember from last class, we had that S naught was equal to 2 I naught. And remember the I naught came from this first filter, which was an isotropic filter, passing all states equally. So we can think here and that transmits 50% of natural radiation. So now S naught is 2 I naught, so we get rid of the 50% by multiplying by 2. And so what we would have here, S naught is equal to A sub x squared, average, let's say, A sub y squared average. Okay, so that would be our expression for S naught. Just the total amount of light present is all it is. S1 is a little more complicated. S1, remember from your notes, was 2I1 minus 2I naught. So I1 came from this linear filter, a linear polarizer, with a transmission axis horizontal. So we could write here 2I1. We could write that as 2, it was a linear polarizer, horizontal, so 2 A sub x squared. And then we have to subtract out 2I naught, so I will subtract out this quantity up above, A sub x squared plus A sub y squared. And I'm going to be left then with an A sub x squared, 1 left over. And I'll show an average here, plus an A sub y squared. And I think I've made a mistake here. That's not a plus, that's a minus A sub y squared. So the A sub x squared minus A sub y squared would be S1. S2. Yeah, each one of these seems to get a little bit more complicated than the previous one. S2 was 2I2 minus 2I naught. And I2 came from this linear polarizer at 45 degrees. Transmits I2, we said. So we could write this as 2 times 1 over square root of 2 A sub x plus A sub y e to the I phi, because remember we have this linear polarizer in at 45 degrees. And maybe I should do this, square that, time average of that, and then minus, well, 2I naught, so minus A sub x squared plus A sub y squared. And so this then will be equal to, well, I'm saying I'm going to square this. I'm going to find the intensity. So the question was, what was this bar right here? And so I'm finding the intensity. So I found the components along the 45 degree, and then I'm going to square this. So I'd get a 1/2 and A sub x squared and A sub y squared and a 2 A sub x, A sub y cosine of phi. And so when I subtract this out, did I answer your question?
Is it just 2 times that quantity squared?
Yes, that's right. I'm trying to find, that's 2 times this quantity squared here, taking the absolute value, because this is a complex, and I want to find the irradiance. So I had to take the absolute value of it here.
Okay.
And so now when I do all this, I'm going to be left, well, this will cancel out 2 parts of this, and I'm going to be left with 2 A sub x, A sub y, cosine of phi. So the a sub x squared cancels, a sub y squared cancel, and I'm just left with the cross term here. So that was S2. S3. Well, S3 is more complicated here. S3 is 2I3 minus 2I naught. I3 came from this filter, which was a circular polarizer, opaque to the left-handed state. So what we're going to have to do for this is I'm going to go ahead and use a little bit of Jones calculus to solve for S3. So let's write that down here. So we're going to have a right circular polarizer, which if we go back and look in our notes would be 1I minus I1 and a 1/2. So that's a right circular polarizer. And the initial polarization we write as a sub x, a sub y, e to the I phi. And so what we get through this filter then is 1/2 a sub x plus I, a sub y, e to the I phi. And then this is minus I, a sub x, plus a sub y, e to the I phi. And I'll just rewrite that as, well, I forgot the little 1/2 out in front here. 1/2, you can read my writing, 1/2 here, times a sub x plus a sub y, e to the I phi plus pi over 2. So we just put that I up here. And down here we'd have minus I times a sub x plus a sub y, e to the I phi plus pi over 2. And so the resulting intensity here, or radiance if you like, we can write as 1/4 when we square the 1/2, and then we're going to be adding the irradiance for here and for here, so we're going to get a 2. And then we're going to get what, an a sub x squared plus an a sub y squared plus a 2 a sub x, a sub y, cosine phi plus pi over 2. Running out of space here, so take a bracket for here and then the time average. Oops.
Where did that extra, in your second step there, where did that extra phase factor pi over 2 come from?
Okay, the question is, where did this pi over 2 come from here? We had a minus I times here, and so I factored out a minus I times the whole thing, so I had to compensate for it here.
Oh, what about, okay, never mind. Okay, thanks.
Okay. Now this, the cosine of phi plus pi over 2, you could write as minus sine of phi. And so we would have here that S3, so now we have to subtract out, remember S3 is 2I3 minus 2I naught. And so S3 here will then be minus 2 a sub x, a sub y, sine of phi. So after a little bit of work, this is what we get for S3. So we have written down S naught, which is just the total intensity, total amount of light. We had the S1, the S2, and finally we got S3 here. So any other questions on how we went through this to get these results? And I'm going to state a few things here about the Stokes vectors. And so if the beam is unpolarized, S naught, well, it's a sub x squared plus a sub y squared. But the real thing is, if it's unpolarized, that S1 will be equal to S2, will be equal to S3, will be equal to 0. So if for an unpolarized beam, S naught gives us the total amount of light, and all the other S's will be equal to 0. Now often we will normalize the Stokes parameters by dividing through by S naught. So often normalize Stokes parameters by dividing by S naught. So S naught is just the total amount of energy, so it's nice to normalize that out. And if you go through here, then it will turn out that for completely polarized light, it will turn out that S naught squared is S1 squared plus S2 squared plus S3 squared. And we often define something called the degree of polarization. So we'll say V is equal to degree of polarization. And V is defined as the amount of light that's polarized divided by the amount of light that's polarized plus the unpolarized light, so divided by the total amount of light, and that will turn out to be equal to the square root of S1 squared plus S2 squared plus S3 squared, square root of that, divided by S naught. Okay. Now, these Stokes parameters, if we are useful when we talk about incoherent, partially polarized light. Question? Oh, okay. So I'll just repeat it here. V was equal to I sub p over I sub p plus I naught, which was equal to the square root of S1 squared plus S2 squared plus S3 squared divided by S naught. So what we want to do now is to look at how we might use the Stokes parameters, and then we're going to have to go on to something else that we're going to call the Mueller matrices. Get it copied?
No.
Nope. Okay.
I'm sorry, I write slow.
Okay. I'll drink coffee then while you write. How's that? So for an incoherent beam, the Stokes parameters are going to add. So let me write that down here. For incoherent beam, the Stokes parameters add. And so, I mean, S naught triple prime was equal to S naught prime plus S naught double prime. And, well, same thing we'd write for S1. And S2, might as well do it. And S3. So we can just add the Stokes parameters. And of course, generally we write this in a vector form, that S is S0, S1, S2, S3, so on. Oh, these are just, okay, the question is what are the primes here? I'm just saying that if I had one beam that's identified by S0 prime, S1 prime, S2 prime, S3 prime, and a second beam S0 double prime, S1 double prime, and S2 double prime, S3 double prime, that when I add these two beams, the resulting Stokes parameters are this S0 triple prime, S1 triple prime, and so on. So I could just add the individual Stokes parameters. Now, just like when we had Jones calculus, we had these Jones matrices that were associated with polarizers and retarders, whatever. We're going to have a similar thing here that are going to be called Mueller matrices. And let me just, before we write down just what the Mueller matrices are, let's just state some things here. That Mueller matrices, when we look at them, M-U-E-L-L-E-R matrices, can be used with polarized and partially polarized light. Okay? They really are giving us the intensity or the irradiance of the beam. The Jones matrices, which you are now all experts with after doing your homework, they're good for coherent light. And they keep track of the phase. So Jones keep track of phase, which is nice in interferometry. Mueller matrices do not keep track of the phase. But they will, well, they don't keep track of the phase. I mean, they're nice for partially polarized light. But if you have completely polarized light, you want to keep track of the phase, they just don't do it for you. And so the Jones matrices are associated with the amplitude. And the Mueller matrices are associated with intensity. So. Okay. So what I want to do now is to look at, well, we'll first look at some Stokes vectors, and then we'll look at the Mueller matrices. And this goes back to a handout that I gave you, I don't know, a couple classes ago, I guess. It's also on the website if you lost it. It's also in our library too, I guess. But Stokes vectors, maybe if we could zoom in a little bit here. First off, I mean, with the Stokes vectors, we had 4 of these guys we have to worry about. And remember, the first one here was the intensity. And if we have unpolarized light, and we'd normalize this to 1, the other 3 guys would be equal to 0. If we have linear horizontal light, then this will turn out to be 1, 1, 0, 0. And you can go back and look at our definitions to see if that makes sense. Linear vertical, well, this would turn out to be 1, minus 1, 0, 0. And again, you can go back and look at the definitions and see if that works out okay. If we have then linear at 45 degrees, that would turn out to be 1, 0, 1, 0. Minus 45 degrees is 1, 0, minus 1, 0. So all these have 1 at the beginning because that's what the total amount of light is normalized to. Right circular, 1, 0, 0, 1. Left circular, if you play with the equations, you'll see that that's equal to 1, 0, 0, minus 1. So those are the Stokes vectors here. If we go to the Mueller matrices now, and I'm not going to attempt to prove any of these to you, but of course the interested student may prove it to himself. But it will turn out that if you have a horizontal linear polarizer, well, first off, I mean, we have a 4 by 4. Nice thing about Jones, we had 2 by 2, so we have more work here. But we have 4 by 4, often a lot of zeros though. And it will turn out that a horizontal linear polarizer is 1/2 times 1, 1, 1, 1. Everything else is 0. And I give the expression here for the vertical linear polarizer. So it becomes 1 minus 1 minus 1, 1 in zeros. And we have the linear polarizer at 45 degrees, which I'll let you read for yourself. The linear polarizer at minus 45 degrees is this. So those are polarizers. Now if we go to wave plates, I guess I could just give you a couple of them here. A quarter wave plate with fast axis vertical is this mess right here. Quarter wave plate with fast axis horizontal will turn out to be this mess. And if we want to deal with things at other angles, just like with the Jones calculus, we have rotation matrices here. 4 by 4 matrices, and look like this here. 1, 3 zeros, a 0, and then a cosine 2 theta, sine 2 theta, 0, 0, minus sine 2 theta, cosine 2 theta, 0, and then 3 zeros and a 1. And they work pretty much the same way that we used them in Jones calculus, that you first would rotate, multiply by the whatever the matrix is for your element, and then you have to unrotate. And so it's similar as what we had before, but a little more work because it's 4 by 4 instead of 2 by 2, but I guess if you do it on the computer, it's no more work really, except you might have to type more numbers in. So those are the Mueller matrices, and as I said, they are useful in working with either polarized light or partially polarized light. They do not keep track of the phase, and they work pretty much the same as what we did with the Jones calculus. Now I have a couple of examples here I thought I would show that's kind of interesting. So let's go through these. So, example here, example 1. So what we're going to do here is that we're going to take light that is unpolarized, unit irradiance, and we're going to pass it through a linear horizontal polarizer. So I'll write that down. Pass unit irradiance. I would actually like to say unit intensity, but I have some of my friends in optical sciences nearly kill me when I say that, so I'll say irradiance. But anyway, unpolarized, wave through a linear horizontal polarizer. So we start out here, we have unit irradiance unpolarized, so that's 1, 0, 0, 0. And we're passing that through a linear horizontal polarizer. So if I look at my notes, that would be a 1/2, and then a 1, 1, oops, 1, 1, 0, 0, 1, 1, 0, 0, and then a whole bunch of zeros. And if we multiply that out, I need help. What's the first element here? 1, there's a 1/2 out in front, so I'll actually bring that inside. So it's 1/2. Second element, 1/2. Next two I can do myself, 0, 0. So what does this say? Well, the irradiance is now equal to 1/2. And that, that makes sense. We had unpolarized light going through a linear horizontal polarizer, so you would expect half of it to go through. We get that. The next thing is that this is horizontal because this is greater than 0. I mean linear polarization, I should say. Linear polarized horizontally since S1 is greater than 0. Okay, so that wasn't too hard. Okay, give you a second to finish writing that down. I'll drink some coffee. So did anybody go to the basketball games? I missed both of them. I was out of town, but one of you did. Anyway. Exciting game? Yeah, all right. Be more exciting this Thursday, I would guess. In fact, we may stop talking about basketball after Thursday. Okay, second example. Let's say we have a partially polarized elliptical wave. And we can write that down here. Well, we'll just write it down, 4, 2, 0, 3. And this will represent our wave, partially polarized. We say it's partially polarized because if we write the degree of polarization here, remember that's going to be the square root of the sum of the squares of these guys. That's the square root of 4 plus 9 divided by the first guy here, 4. So square root of 13 over 4, according to my notes, is 0.9 roughly. And so it's partially polarized. Now, since S1 is greater than 0, it's more nearly horizontal than vertical. Okay, so we see that. And S3 is greater than 0. So right-handed it will turn out. And it also turns out since 3 is close to 4, this is nearly right circular. Okay, so now what we're going to do is we're going to take this beam, which we have these little things that we've noted about it. We're going to take this beam and we're going to transmit it through a quarter wave plate with a vertical fast axis. So let's write that down here. So transmit wave through quarter wave plate with vertical fast axis. And we're going to see what that does to it, okay? So we have this guy here that was 4, 2, 0, 3. And we're sending it through a quarter wave plate. And if we go back and look in our notes, that turns out to be a 1, 0, 0, 0, 0, 1, 0, 0, and before you even think about I don't even want you to even think about memorizing these things at all. Just, you can always look them up. 0, 0, 0, minus 1, and a 0, 0, 1, 0. And if we multiply that out, oh, I really need help here. What's the first guy going to be equal to? Oh, that wasn't too hard. Second guy, 2. Oh, that wasn't too hard either. Third guy, minus 3. Yeah, that wasn't too hard. Fourth guy, boy, that wasn't hard at all. Okay. So, what has happened here? Well, we have the same irradiance. We had a normalized thing. It's 4. Same irradiance. Well, I mean, that makes sense. You transmit this wave through a quarter wave plate. You don't, I mean, it shouldn't change the irradiance. How about the degree of polarization? V would be equal to square root of what? 4 plus 9 over 4. Ah, same thing we had before. So same degree of polarization. And again, that's no surprise. You send it through a quarter wave plate. Shouldn't change the degree of polarization. Let's see, before we had a partially elliptical wave. In fact, we said it was close to being right circular, but it was elliptical. How about the state of polarization here? Is it elliptical? Well, this guy is 0. And these guys, which are polarization, linear polarization at 0 and 45 degrees, are there. So what we have now is not elliptical, but it's linear. Okay. Which again will kind of make sense. We send stuff through a quarter wave plate, and we can convert elliptical into linear with that. So this is now linear polarized as opposed to elliptical. Anyway, those are just some examples of what you can do with the Stokes vectors and the Mueller matrices. And they kind of complement what you can do with the Jones calculus. So any questions on Chapter 3 on polarization? This concludes everything we're going to cover on Chapter 3. Well, I said earlier that when I started this chapter that officially this polarized light is not to be covered in this course, but I've found on prelims over the years that students are often weak in polarized light, so that's why I add a little bit here. So if you have me on prelims, maybe I'll find out if it's worked or not, and find out if you're now strong on polarized light. Okay, well, let's get back to kind of the main, more of the main stuff for this course, which is, interference and diffraction. And so it takes us to Chapter 4, which actually has a title of interference. So let's see what we have here. And so what we're going to do is we're going to interfere 2 electric fields in this chapter. So it's interference of 2 wavefronts. Two electric fields, E1 and E2. And of course we have to remember that these are vectors. And so let's say the 2 electric fields, one we're going to write as E1, magnitude, and also get the vector in this. And it has a phase of e to the I phi 1. And the second guy is some E2, e to the I phi 2. And we're going to be interested in the irradiance, so we'll take the magnitude of this and square it. And so what we get here is E1 squared, and we're going to get an E2 squared, and then we're going to get the cross terms, which will be an E1 dot E2.
Is this supposed to be E2 squared or E2 vectors?
Oh, it's an E2. Yeah, you're right. The question was, what was I supposed to be writing here? So it's E2 and then squared. So it's E1 squared plus E2 squared. Plus the interesting part here, which will be the cross terms, which would be the E1 dot E2 times e to the I phi 1 minus phi 2 plus e to the minus I phi 1 minus phi 2. Okay. And the way we normally will write this is that I, the radiance, is given by E1 squared plus E2 squared plus 2 E1 dot E2 times the cosine of alpha. This simply becomes twice the cosine here. Cosine of alpha, where alpha is the phase difference. Whatever the phase difference is, this is the expression that we would get. Now, get some more paper here. This is almost related to a homework problem that you've already done. But if A1, so let's say that, let me rewrite this. I'll just rewrite this as I is equal to I1. So it's the radiance of one beam plus the radiance of the second beam plus 2 times the square root of I1, I2. And then we would have an A1 dot A2. So A1 is the direction of E1, A2 caret here is the direction of E2, cosine of alpha. Now if A1 is perpendicular to A2, so the two electric fields are at right angles to one another, we get no interference. This term would go away. And our course would be very short if we were in that situation. Okay. Now, if they're not perpendicular, we're going to get interference here. And we're going to get fringes that are going to have some shape. And we're going to get a bright fringe, assuming we have interference, that the bright fringe when alpha, whatever the phase difference is, alpha is equal to what? 2 pi times some integer m. Okay? And m is what we call the order number. Question? Yeah, if this is true, we have no interference. End of that. Now we're down here, we're assuming that these are not perpendicular, so we do get interference. And if we get interference, we're going to get a bright fringe when alpha is 2 pi times some integer m, and m is what we call the order number. So m is called order number. And now we're going to get a dark fringe. So we get a dark fringe when we're going to get a dark fringe when this cosine of alpha is -1. And so we're going to get a dark fringe when alpha is 2 pi times this some integer, m, plus a half. Okay? Because we want an odd number of pi's in alpha for the cosine alpha to be equal to -1. Now what we're going to do in this whole chapter here is that it's simply we're going to determine alpha for different situations. And what we're going to do is we're going to determine alpha for first thing will be 2 plane waves. So we'll determine alpha, and from that, then we'll determine the shape of the fringes. After we do 2 plane waves, we'll look at 2 spherical waves. And then after we do 2 spherical waves, we will do a plane wave and a spherical wave. Okay. And then the last part here is that we will do a plane wave and a cylinder. So those are the 4 sections, and then there will be another section on combining beams. But the first thing is to determine alpha for these 4 situations. Okay. I'll take a sip of coffee and give you a chance to get all that written down. Okay, so now let's go ahead and look at 2 plane waves and see what we get. Get that out of the way. So this is section 4.1 called 2 plane waves. And so let's just write down this. E1 is just some magnitude E1. E to the I, K1 dot R minus omega t plus some phase phi 1. And the direction is some in the direction of this unit vector A1. The second plane wave has some different magnitude, E2, E to the I, K2 dot R. It's going to be going in a different direction. It's going to be the same frequency, though, make life simple for us here. Although we can comment on what happens if it's not the same frequency. So we'll make that omega t plus some phase phi 2, direction of A2. Now we have a whole section coming up here later on coherence, so I won't go into that now, but I'll simply say that if phi 1 minus phi 2 is equal to a constant, the 2 sources are said to be coherent. 2 sources are said to be mutually coherent. So the next thing we have to do is kind of look at these K's here, what we get. And we're saying that, I'll first write down what they are and then we'll make a little sketch here. We'll say at K1, so the propagation vector K1 is equal to K, which is just 2 pi divided by the wavelength, times the cosine of, yes, question? Constant in time. Not only, so the question is, what do I mean here when I say that phi 1 minus phi 2 are constant? They're constant in time, but they're also going to be constant in position. And how the phase changes in position will be taken care of by this k1.r and this k2.r. So it's constant in both time and phi 1 minus phi 2 are constant in both time and position here. So this is k times cosine of theta 1 in the x direction plus sine of theta 1 in the y direction. And the second k here, we're going to, and I'll sketch this in a second. Second k is k2, is k again, 2 pi over lambda, same wavelength, cosine theta 2 in the x direction, plus sine theta 2 in the y direction. And then the other thing we'll say is that r is xi plus yj. And that's what we call, I think we said before, the position vector. So let's sketch these k's. And sketch them in red. So x and y. And so one of these k's is like so here. And let's say that's k1. And so this angle here, measured in this direction, would be theta 1. And so if we go back here, we said that k1 was k, 2 pi over lambda, times the cosine of theta 1 in the x direction, plus the sine of theta 1 in the y direction. And then the next one here, the k2, just at some other angle here. And this is now an angle theta 2. And again, k2 was k cosine theta 2, x direction, plus sine theta 2 in the y direction. And you can note my sign convention the way I've pictured it. Okay, so remember, now we're going to look at these interference fringes, and we want to determine the shape of the fringes. And we said that the position of the fringes depended upon this alpha. We got a bright fringe when alpha was 2 pi times some integer m, the order number. And so what I really have to do now is to determine what alpha is. So let's do that. So alpha is simply the phase difference between the two beams. I'll write that down. Phase difference between two beams. And so alpha here is k1 dot r. And so one beam was k1 dot r plus phi 2. Phi 1, excuse me. The other one then is k2 dot r, so we have k1 dot r minus k2 dot r minus phi 2. Now, if the frequencies were not the same, then we also would have a term in here that would go omega 1 times t minus omega 2 times t. So we'd have something that would end up being omega 1 minus omega 1 minus omega 2 times t. But we're saying the frequencies are the same. So we're just left with this right here. And so going up to what k was in a previous piece of paper here, we would have this is equal to k, 2 pi over lambda, times x, well, maybe I should put x times cosine theta 1 minus cosine theta 2 plus y times sine theta 1 minus sine theta 2. plus phi 1 minus phi 2. And for a bright fringe, whatever this mess is, that's equal to 2 pi times order number m for a bright fringe. Okay. And for a dark fringe, get my paper here. So that's equal to 2 pi times m plus a half for a dark fringe. Okay. So looking at this expression here, knowing that phi 1 minus phi 2 is just some constant, that would be the equation of what type of curve? That's the equation of a, is that the equation of a circle? I hope not. Ellipse? No. What? That's just the equation of a straight line. Okay. Therefore, we have straight line fringes. And the position of these fringes is determined by this equation right here. Okay. Now let's, for a second, let's say that phi 1, any questions on that before we go on? That's pretty simple, but very, very important here. Okay. Now if, let's say for a second that phi 1 minus phi 2 is not a constant. Let's say that phi 1 minus phi 2 varies in a random fashion over the integration time. So phi 1, for a second, let's just assume that phi 1 minus phi 2 vary in a random fashion over the integration time.
So the phase difference in these alpha is not necessarily just always phi 1 minus phi 2. It's got the...
No, the phase, the question is, what is the phase difference in the alpha? The phase difference in the alpha is the total phase difference. It's, if we go back, it's going to be whatever this phase is here minus whatever that phase is there. And what we're looking at right now is simply the situation for plane waves. And we get this expression here for the alpha, the phase difference. But when we get to spherical waves, we're going to get something else for alpha. But alpha, the thing to remember here, this magic alpha is always, you know, for a bright fringe, whatever alpha is for a bright fringe is always equal to m times 2 pi. Now, we were saying before that phi 1 minus phi 2 was a constant, but let's just for the time being, let's say they're not a constant. Let's say it varies in a random fashion over the integration time. And so what's going to happen? Well, it's going, the fringes are going to wash out. And so if this varies in a random fashion over the integration time, we will have no interference fringes. So we will have no interference fringes since the mean value of cosine alpha is 0. Okay? And when we talk about incoherent light and so on, we'll have these situations where this phase does vary over time in a random fashion. But right now, for the rest of this section here, I want to assume that phi 1 minus phi 2 is equal to a constant. Okay, so now we have the general equation for these fringes. Now I want to look at these straight line fringes in a little more detail. And then I even brought something here where I can demonstrate the fringes. So let's look at this in a little more detail here. So I'll say a special case. And a special case is going to be the following. Well, first, let's say phi 1 minus phi 2, let's say it's equal to 0. Now, if phi 1 minus phi 2 is not equal to 0, what do you think that's going to do to the fringes? Is it going to change the shape of the fringes? No. But it will cause the fringes to move. Okay? So if phi 1 minus phi 2 is not equal to 0, the shape of the fringes will still be the same, but they will move. So, I want to keep life as simple as possible, so we'll say that's equal to 0. Also, I want to make life simple for me. So I'm going to look in the x equals 0 plane. Okay. So that will simplify my expression for alpha here if I put in that x is equal to 0. So I could pick my coordinate system such that x is equal to 0. So now what we would have is that the irradiance I is I1 plus I2 plus 2 square root of I1, I2. And I guess I better not forget the A1 dot A2. And then I'm going to have a cosine. I never have enough space, it seems. So the cosine of ky, so, times sine theta 1 minus sine theta 2. Okay? So cosine of ky times sine theta 1 minus sine theta 2. And so maybe the first question I want to look at, I'm going to look at bright fringes, and I'm going to say, what is the spacing of these fringes? We know we have straight line fringes. What is the spacing? So what is fringe spacing? Well, for a given fringe, this is equal to an integer times 2 pi. And if I go to the next fringe, this is going to be, it's going to change, the integer number will change by 1. So what I can say here is that k, 2 pi over lambda, times y, times the sine theta 1 minus the sine of theta 2 is equal to some integer times 2 pi for a given fringe. And I could cancel out the 2 pi's, and I could say that m times lambda for a given fringe is y times sine theta 1 minus sine theta 2. And if I go to the next fringe, so that's for one fringe, if I go over to the next fringe, I would have m plus 1 times lambda is equal to y plus delta y times sine theta 1 minus sine theta 2. And so delta y here, from these two equations, delta y here will be equal to lambda divided by the sine theta 1 minus the sine of theta 2. And that's important enough, I'll draw a red box around it. Okay. And I'll celebrate by taking a sip of coffee. Okay. So, first off, the fringe spacing depends upon the wavelength. The longer the wavelength, the larger the fringe spacing. So, if I keep these angles fixed and I go from blue light to red light, the fringe spacing is going to become larger. Okay? The next thing is the larger the difference in the angles, or maybe I should say the larger the difference in the sines of the angles, the smaller the fringe spacing will be. So if I have two beams that are nearly parallel to one another, the fringe spacing will become fairly large. And if I increase the angle between these two beams, then the fringe spacing is going to become smaller. Okay? Kind of interesting anyway. And just for the heck of it, let's say theta 1 is minus theta 2. It's equal to theta. And so we have kind of the symmetrical case here that we have one beam coming in here, theta, and the other beam's coming in up here, theta. And now we would have that delta y is lambda over 2 sine theta. Okay. Now there's one other quantity. I have a view graph I want to show, but one other quantity I should talk about first. This is a spacing of the fringes. Delta y is a spacing of the fringes. And if I look at 1 over delta y, so 1 over the spacing of the fringes, I'm going to call that the spatial frequency of the fringes. S-P-A-T-I-A-L, frequency of fringes. Okay. And the one view graph I want to show, this comes from those interference view graphs that probably many of you have copies. All I've done in this view graph is I'm plotting this, or this equation right here. And I'm plotting, well, I'll show it here and I'll show you precisely what I'm plotting. So I'm plotting the spatial frequency, so I'm plotting 1 over that. And I've done it for two situations here. One is the symmetrical case, except here I call it phi over 2 instead of phi. So the total angle here is phi. And the other one is where one of the beams is normal, and the other one is off at an angle phi. And I picked a wavelength of 633 nanometers. Why would I pick that wavelength? It's a helium-neon laser wavelength, okay. And I just made a plot here of spatial frequency, in other words, lines per millimeter, as a function of angle phi. So for both of these situations here, 1 and 2, the total angle between the two beams is phi in degrees. And if I go here to like 45 degrees, I get a number over here that is greater than 1,000 lines per millimeter. So these little fringes can get pretty close together. Now if we go down here to 10 degrees, now we have a spatial frequency of, I don't know, 200, 230 lines per millimeter or so. So the point I'm trying to make here is that using light, which has a short wavelength, if the angle becomes large at all, the spacing of these fringes becomes very, very fine, very small. Okay, any questions? Well, one last thing I'd like to do, and today anyway, is to kind of look at this physically, what is happening, and I hope I can do that in 5 minutes. And then what we'll do next class, we'll actually see some interference happening here in class. And so this is just a little physical explanation as to what is happening. So what we have here is that we have two beams interfering. One beam like so. And another beam at a different angle. And we can draw perpendiculars between two rays here. Supposed to be perpendiculars anyway. And so one of these guys makes an angle of theta 1, And I guess for my drawing here, I actually make that the larger angle, theta 1. And for my drawing, the smaller angle here is theta 2. And let's say these guys are in phase right there. Okay? If I look here, and say this distance here is delta y. And so what is this path difference right there? Well, if the angle here is theta 2, distance there is delta y, then this path difference right there is delta y sine theta 2. So that's this length right here. This path difference right here, then, is going to be delta y sine theta 1. And so the optical path difference for these two beams at this point, say they match here, at this point the optical path difference, OPD, is delta y sine theta 1 minus delta y sine theta 2. Okay? And so we're going to get a bright fringe. Say these guys are in phase here. We're going to get a bright fringe up here when this is equal to lambda, well, some integer number of wavelengths, m lambda. Okay? So that kind of physically explains what is happening here and why we get bright fringes or dark fringes or something in between. Now the last thing I might say here in my remaining minute and 38 seconds is that these fringes, we have two plane waves coming in. These fringes are existing every place that these two plane waves overlap. And you might say, well, so I kind of think of like we have fringe planes here. And we could go through some math and show where these fringe planes are. But if you just think physically for a second here, is that there's no reason why these planes of fringes here would be closer to the direction of one beam than to the direction of the other beam. And so these fringe planes that exist in space actually will bisect the angle between the two interfering beams. Okay? And so if I had the situation here of the symmetrical situation, one beam coming in here and the other beam coming up here at the same angle, now these fringe planes, which bisect the direction between the two beams, would actually be normal to the observation plane. Well, I'm afraid my time is up here for today. We'll come back to this at the beginning of next class. We will then talk a little more about these fringes, and I'm going to give a little demonstration of interference in class. And then we'll go on and talk about spherical waves and plane waves. So I'll see you bright and early Thursday morning.